The most time-consuming part of designing a chip isn't the design, it's making sure that it works. So hello everyone, today we have 18-year-old students who have created AI software for hardware, and one of them has joined Stanford and one of them is taking a gap year, and they created it before joining Stanford, and they've been building stuff since the age of 16. Today we'll get to know about the journey, the future of semiconductor industry, how they got inspired to create something for the chipset ecosystem, and much more. So hi Sathvik and Jag, can you please introduce yourself?
Yeah, hi, I'm Sathvik. Me and Jag have really been working on this kind of thing since 5th grade. We were both best friends since then. And I just graduated high school a few months ago with Jag and going full time on building this EDA startup.
Yeah, and I'm Jagmati Patla, co-founder alongside Sathvik. I'm a current Stanford student doing electrical engineering. Sathvik and I, as you said, we've known each other since like elementary school. We've been building rigorously since then. But yeah, we both grew up in Virginia, came to California just to work on this project. So they've been working on the EDA startup, which is electronic design automation, which is the automation for the chipset ecosystem. We'll get to know about all that. But first, can you please share what inspired you to first create a chipset company? So before creating GetInstaChip, which is, the EDA for chips, what inspired you to create a chipset company when you all started at the age of 16, I believe, right?
I think we should probably take it's different for both of us, right? So for me personally, it was like a curiosity in the software space, right? So I started really into software. When I was 7, I was making, games. And then when I was 12, I was making compilers. And then from there, it was going lower and lower and lower into the software stack. So I was really trying to understand how hardware actually worked, down at the fundamental level. So that's when we started Photonics, which is using light instead of electricity to do computation. So at the fundamental atomic level, how do you make software faster at the hardware level? And that's when me and Jag started talking about actually, creating and taping out some of these chips.
Yeah. And I mean, the motivation for me is pretty different actually. I think from a very young age, I was dead set on medicine. So I wanted to become a doctor, specifically heart transplantation sort of side of things. Tech was something that I got into only with respect to medicine, so biomedical engineering. But I thought that irrespective of whatever field you go into, it's necessary to understand how computers work from the electron up, because they run our world nowadays, right? That's crucial. So I got into that, and I was looking into the hardware side of things 9th grade, trying to figure out exactly how it worked from the electron up. And yeah, as Sathvik said, those conversations started up. They started going places, and we started looking to different computing paradigms and settled on photonic computing. Can you break down photonic computing? What is it? For sure. So in essence, right, photonic computing is just the process of computing with light instead of electricity. So the data is encoded in the photons, specifically the brightness of the photons, as opposed to electric signals, like the binary zeros and ones.
Right. I see. So instead of saying is your signal on or off, you use the amplitude of the electric field of the photons or the lasers that are firing. So instead of having wires that plug into electrical outlet, there are literal lasers that are inside your computer that shoot beams of light. And then how the square root of how bright the light is literally what the data is representing.
Exactly. So based on how bright the light is, you can say it's 1 or 0. So you can basically transmit data and electricity.
Or not necessarily actually. So you don't even you just throw aside ones and zeros. You just say literally what is the value of how bright it is. And that value is then used to do computation like matrix multiplication. And at the very end, that's when you change everything.
So it's analog basically.
Yeah.
I see.
Yeah.
So the data is transmitted through photons.
Yeah. That's, more or less, yeah.
Okay, pretty cool. Okay.
Just like how inspiring is the journey of Sathvik and Jag, it is also of the app called Moomoo, which started from Palo Alto, California as well, and has reached almost 23 million users. And I use it every single time I look at the market trends, or if I have to look at China and Hong Kong's market, because there are rarely stock brokerages apps in America like Moomoo which allow you to invest in Hong Kong's or China's stock market and look at the level 2 data with that much information. And just like 62% of Americans in the US who have a stock brokerage account, you can be one of them. It's completely legal on F1, H1B visa, and get started immediately by going to start.moomoo.com/singinusa and get up to 15 free stocks and 8.1% APY. Go start right away.
Now, can you share what kind of students
or like your peer group you surrounded yourself with to get into hardware engineering? Because I know that coding is taught in schools these days. People learn at the age of 7, 8, 9. But how did you get into hardware? Was it just because of your personal interest, or you were surrounded by great hardware enthusiasts?
I think it's a mix. Again, like it sort of started like, out of personal interest, both me and Jag ourselves, but also like, the high school that we went to was really like STEM focused, right? So, everyone was sort of doing like some sort of thing. Like we had, like quantum electrodynamics classes and things, and we even have a lithography machine. So it's like everyone is like doing like this kind of thing, maybe not in hardware, but in something. Everyone wants to be like, the best in like what they're doing. So this sort of is like a drive, like when you're surrounded by like an ecosystem of like everyone who's like that, you sort of want to be like that yourselves. And I guess for me and Jag, that was like hardware and like.
I see.
Yeah. I mean, same for me as well. I will also go like further and say that if there wasn't, another person to like talk to and like engage discourse with about like hardware, I don't know if it would have gone like too far, because you really need another person, to speak with and like discuss ideas with and build upon. And yeah, I think that's crucial, irrespective of what you.
Totally. I think when you have someone as an accountability partner, you can innovate together, because I think every single time innovation has happened, it has happened when people come together. Now, getting into the chips, the first company you all created was a chip company. And can you break it down? Like, what inspired you to create chips? Because like the competition is really big. And I saw your tweet, especially you said, if you want to create chips, your competition is not with NVIDIA. Your competition is with OpenAI.
Yeah. I have a lot of thoughts on that.
So can you break that down as well?
Yeah, for sure. I think first we can start with, why did we start the chip company? Like we both said, it was personal curiosity. Why did we choose to evolve that into a company, right? So we were sort of dead set on like, how do you make the fastest computer, known to man? But the, like what we thought that was like, we go into our computer, like our garage, we have like a bunch of nuts and bolts and like giant magnifying glasses and like lasers, and we like shoot them around our garage. And we couldn't be more wrong, right? Like we realized actually studying this sort of stuff for like, at that time, a few months, we realized it was all in silicon photonics, which is like photonics lasers on a chip. Then we got really interested in like, chipsets and chip architecture and all of that. And at that point in time, we realized like, if we have something like photonics, people are not going to be using it to like open a new tab or something. They're going to be using it for AI workloads. And at the time, there were, other startups doing similar technology, but we thought that, by having the technology that's like substantially like, really good, faster, like and more energy efficient, we could break the market with our technology. So that's why we started to form it into a startup.
And to add on to that, right, the time that we started, I guess like the time that we decided to move into a startup phase was sort of like right. In the AI space. This was like, I would say 2021. So just when the AI boom was starting and when we had a compute gap. So we really saw a need for this in the world. Obviously, like since then, a lot has changed. Right as we were working on it, there's an explosion of other companies as well working on hardware. So we knew that we were at the right space at the right time. And yeah, that's just like more evidence.
How does, so photonics is already being used in chips right now, or you were one of the few people who wanted to get it integrated?
A little bit of both. So photonics are a thing, right? Like photonics as a technology have existed for like decades. And photonics for compute, on the other hand, like the research in that has also existed for decades. But actual startups doing photonic computing, that is like a very small number. Light Matter is like one of the most successful ones. Today, they're over $1 billion. But there are other companies like Luminous who's doing photonic computing. But we were sort of like, I guess, one of the few that were doing photonic computing. And we were also one of them that unfortunately didn't work out. So
interesting. Oh, go ahead.
Yeah, no, like it's basically as he was saying, like photonic computing is something that has existed for many, many years. And actually the exact tech that we were using is something that was created in like laboratory settings in universities back in 1980. Like it's nothing new. But the reason why it didn't scale any further than that is, well, two reasons, right? Number one, the tech that we have right now to make chips, it was like not as precise back then. So they couldn't scale what they had into the nano scale, like chip level. And secondly, there's a big prioritization by like the government at that time to work on decryption, encryption, cryptography, specifically like for wartime capabilities. So with respect to that, like a lot of companies at that time that were focusing on computing switched gears because the time was ripe for them to work on cryptography and decryption.
How does photonic compute in chips is better than the previous, how do chips are made? It's analog, right? Photonic is analog.
Correct. Right.
And currently the chips are made digitally.
Right. So there are advantages and there are disadvantages. So when you use photonics to do like AI computations, for example, there are two benefits, right? One is it's the speed of light, literally. It's insanely fast. And the second benefit is it's insanely energy efficient. So like that's why we decided to go into that field. But the problem is that once you have like, when you have a chip, you have your input, you have your computation, and you have your output. When you do photonic computing, the computation is really fast, but the input comes from electrical places and the output is fed to electrical places.
Correct.
So when you're reading data from electrical places and you want to convert that to photonic computation, that conversion delay is slower than just using a GPU. So it's not really like worth exploring. And there are some startups like Light Matter who are doing interesting things to circumvent that. And that's why they're worth $1 billion.
I see. And can you share about the traditional ways, how these chips are built, like with digital ways? Like, so the information is coming through in electronic ways, as you mentioned.
Right.
So what do you do in those traditional ways digitally right now? How the chips are being made, especially with NVIDIA or with Apple? How this is happening in VLSI industry?
Well, you have those core buzzwords, right? Like logic gates, transistors. When you think of a traditional chip now, like that is built by NVIDIA, by Intel, it's those electronic circuits that are built with billions of transistors that hold zeros and ones. And like all that comes together to make like logic gates, AND gates, OR gates, NOR gates. And then those are scaled up to build like larger, like I guess more abstracted concepts like matrix multipliers, sparse matrix operators, that sort of thing. And like that is the fundamental tech difference between digital and photonic, because photonic, as you said, uses no transistors, it's fully analog, right? Completely different world. But yeah, that's the core difference. But when you think of a chip right now, those are the buzzwords that you should be thinking: transistors, logic.
I see. Okay. So you're like escaping the route of transistors and logic gates, because there's a huge industry of like, SoC. It's a system on a chip, because a lot of people design that. So how would SoC, like engineers who are working on designing those chips, would be different if they were designing for the photonic ecosystem?
Yeah, I mean, there are like, when you're working with like photonic chips, there are like other things you have to integrate which make it an SoC, right? But the problem is that, what an SoC engineer would do is that they would take like components that convert electronics to photonics, and they would have to integrate those interconnects onto their chips. So what those look like are like with traditional like electronic compute, you have these components called digital analog converters. They take digital signals and they turn them into analog signals where the photonic domains come in. So once you have that analog signal, you can use that to like supply current to your lasers, and then the lasers will like turn on, and then that's when the photonic stuff happens.
Okay.
So you can have all of that on your chip, and it's now like a photonic SoC.
So that's how you created a 20 nanometer chip. How efficient was that when you created it? And why did you have to shut that down?
I think our like efficiency reports aren't like scalable, to be honest. So what I mean by this is that we created a chiplet. It was 7 teraflops technically, right? But the problem is that we created it for like really like small matrix sizes, and when you scale, you lose performance. And so like that 7 teraflops like drops like like this, right? So
what a 7 teraflops? Can you break that down, like for like people who might not understand?
Yeah. It's like trillion operations per second. Floating point operations.
Okay, got it.
So
so it could handle 7 trillion
floating
operations
per second.
7 teraflops.
Right. The benefit is actually energy efficiency over speed. So it was much higher in terms of energy efficiency. But again, I don't want to say either of this because of the reason that I mentioned is that, we use very small matrix sizes, and once you scale to like industry standards, you dramatically start to lose power. So it's not fair to make those comparisons. But at the time, that is like, I guess being like new to the space at the time, that is something we didn't know. So
how did you guys test that much power on a chip?
Oh, we used like probing instruments from this place called Applied Nanotools. It's in Canada. They have a facility that's tied to the University of British Columbia. So you can like supply like, I want to run these specific tests on your instruments, and they'll do it for you. And then they'll send results. And that's really how it's done with like even, TSMC or any chip provider.
So instruments, they have like automated the process of like, putting some payload on those chips.
Well, how the probing system works is you have, so first of all, you have the silicon wafer, right, that you made the pattern on. You put that in this like machine, and it will take like these probes and put them in the inputs of the chip that you define. And then they'll shoot like light through it. So you don't need like any external system. You have like these probes that shoot like all the like millions and trillions of like signals, in light. And then you have like other probes at the end that measure the output. So it's like a very automated like process, and it's a very specific machine that like, sends signals photonically and takes the photonic output.
And how was it integrated? Like, was it a vertical integration with RAM inside the chip, outside the chip?
No. So, the chip itself, as Sathvik was saying, it's like very, very, very specific there. And we didn't even solve the problem of photonic memory yet. That's a completely separate issue.
That's actually an unsolved issue. But
Well, in research, but there are a couple of things right now, in our chip that it simply could not do. It could not store data, etc. But the only thing that it could do,
little bit data.
the only thing it could do was multiply matrices, that sort of thing.
Yeah.
And that too, it was constrained by the dimensions of the matrices as well. And that's a big reason why, I think you're alluding to it, why it failed. So, there were a lot of technological like bottlenecks that we simply could not like pass. Photonic memory is one. This whole like gap that Sathvik was talking about between integrating photonics with electronics, and also loss. So the thing with analog, right, is whenever you have a signal on the chip, as the signal propagates, it's like a little bit of the signal is lost in like noise and whatnot. You don't see that with binary zeros and ones in digital, because it's either 0 or it's a 1. In analog, it's some like value between 0 and 1. So you get like, the more specific that number is, the more data that you can encode on it. But as it keeps going, some of that data is lost. So compensating for that loss is a difficult issue in and of itself. And if you lose too much data, then the output is not at all going to be correct, right? It's not going to represent what the input was. So those three issues, I think, combined sort of made us shelf the photonic computing.
Yeah, because there's ongoing research of converting digital data into analog, especially in this photonic to electric circuits translation ecosystem. So that is not lost yet. That is not lost less yet. So that's why, is that the main reason it's failing?
Well, it's those three, right? Like the loss is an issue. But even if they were to solve that, they need to make sure that you can store this data on the chip, because the only way that this is going to be computationally efficient, right, is if you take all this data and move it onto the chip first before you're able to do the computation. The speed increase is only from the photonics. You actually see a speed decrease when you convert from digital to analog, electric to photonic. So if you're able to move all the data and store it onto a photonic circuit, and it's a closed loop, whereas it like takes the data from on-chip photonic memory and computes, that's beautiful. That means that you're able to bypass that whole like integration. But as long as that problem is not solved, it's not efficient enough.
And that's why people are trying to make photonic memory, because like in order to solve the problem that Jag was talking about, what you need to do is you need to make your digital analog converters have a really high, what's called sampling rate, which means how fast they like interchange, like convert data and signals. So if you don't want to deal with that problem, what you can do is you can have photonic memory, and then you can like, you can like take the bullet and just send your whole network to the photonic chip. And now it's like there already. So you don't need to go back and forth. And then if you're able to like store the weights and stuff somehow in some scalable way, then you can just do all those computations. And then once you're done, have one final like, conversion again. And that is like technically still not optimal, but it's quite, much better than what we have now.
So now finally coming back to the tweet. So you had to shut down the startup, unfortunately, but one day it can be possible once these three problems are solved. Now, why do you think new chipsets have competition with OpenAI instead of with top chipset companies like Apple, Nvidia, etc.?
I actually think this for AI chip companies, right? Like anyone who's making an AI inference chip, AI training chip will not compete with Nvidia. They're going to compete with OpenAI. And the reason for this is because when you create a chip, even if it's like, faster, better, more energy efficient, you're still not going to be able to sell it to like barely anyone. Even like, some startups that are doing LLM specific chips, they have really like trouble like selling these LLM specific chips to any major chip providers. And the reason is because no one wants to trust, like no major person wants to trust like, infrastructure that's used by millions of people on some startup's chip. In the past 12 years, Meta has only sourced from startups 2 times for this kind of stuff. So what this means is that like most companies in this area, what they end up doing is they end up launching an API around their hardware. So and what you do, like if you have a API around your hardware, then you're competing with other people who have, you know, AI model APIs like Anthropic, OpenAI, and your differentiator is now Grok's differentiator, which is supposedly better hardware, right? So can you really compete? Like even if you had like, you know, 10x hardware, and that would mean that your developer experience is really good, but can you compete with OpenAI's distribution? Can you compete with like, you know, Claude's models and like all these things is quite a hard problem to solve. But if you're able to, you know, somehow get your chip past like, you know, major chip maker's doors, that is like a big deal. So
I totally agree. I think they are the biggest competition because there was also data that like Claude, because it was trained on H200s, they were somewhat better for some kind of operations such as coding than even OpenAI is O1 in some cases. So there is a lot of truth that if you have the latest GPUs, you can have better models. Okay, now...
And I think, again, that's way, way more true with O1, right? Because if you look at like, and everyone is saying this, which is now like, it's now inference scaling because they've reduced like the reasoning thing to like, if you look at a graph, it used to be like this much training and then like this much is like inference compute. And now you move all of that to before. And now the inference market, literally you have like a 10x because everyone now wants to make an inference chip. So that's good for us, I guess.
Correct. Now let's get into GetInstaChip, which is the EDA startup you're building. So you got 50K for your chips company. Now you guys are pivoting for GetInstaChip. So can you elaborate on, first of all, getting into the EDA startup, can you elaborate on the VLSI industry that you saw, that you have market, your TAM and SAM, you know these terms?
Yeah.
Like total
addressable
market, and SAM is like the actual addressable, I don't know, I forgot.
The part that you can actually capture.
Yeah, the part of what you can actually capture. So can you break it down?
Yeah, for sure, right? So I think TAM is like, well, so first of all, to break down like how the semiconductor industry works, there's basically like a few like players, but each one of them pays in like it's sort of like a power law, where the ones that are like, you know, at the bottom of the power law, they'll pay you like 500K per contract, which is still a lot. And then the ones in the middle will pay you like 10 million. The ones in the top will pay you 300 to 700 million. So what you really need to do is to lock in such a contract, you have to get in the door with some of these companies in the bottom. And then like once you have them, they don't want to move away from you. So in terms of TAM, what that means is like, it's about 20 billion for FPGAs and ASICs right now.
FPGAs and ASICs?
Oh, the FPGAs are basically like, you know, you can have any circuit, any digital circuit that is represented in real time. And unlike an ASIC is like a chip, right? So unlike a chip, which you can't change, you can change FPGA by like reprogramming it. So the hardware literally changes. But the sort of interesting thing about the semiconductor industry is that it's 20 billion now, right? But it's growing like quite quickly. And so it's like there's a few number of startups, and you know, LLMs for circuit design is quite new. So I think it's really essential for us to capture that like area. And again, like once the semiconductor industry wants you, they don't want to go away from you. They want to like keep your workflows, right? So it's really essential to get that and then scale with these companies that are then growing. So,
and what he said at the end was a crucial point. Once they want you, they don't want to get rid of you. But that works the other way around. Like once they already have a workflow in place, it's very difficult to break in. So that's like when you take a look at these very large companies, right? Apple, Nvidia, when they make a chip, they have like a very like rigid process that they have tried and tested over like last few years that works well for them. So when you come in with a new product and say, we want you to integrate this, it'll make your workflow faster. Even though that might be true, even though it will accelerate their workflow, it's difficult for them to integrate it. So there are some difficulties when you work with larger companies, with respect to that. When you look at smaller companies, maybe the ones that only pay like 500K or whatnot, it's a different situation, right? Because these might be startups, these might be like budding chip companies that are much more open and are much more flexible. So even though, the ultimate goal is to get that top like 0.1% of chip companies because they will be the biggest contracts. The difficulties that come with that are they're sizable.
Much harder than even making a chip.
Yeah.
Yeah.
So FPGAs, I still didn't get it. Can you break it down?
Yeah. So an FPGA stands for Field Gate Programmable Array.
Programmable gate array.
Oh yeah, sorry, yeah, I missed that one.
Okay.
But yeah, Field Programmable Gate Array. So what it does is you can program the hardware of the chip to change, and basically emulate whatever like circuit you're building. So people use FPGAs before they make the actual ASIC.
In what ASIC?
ASIC stands for Application Specific Integrated Circuit. So it's a chip that's made for a very problem. So when you think about a chip being made solely for inference, for example, that's an ASIC. But before you print an ASIC, you need to make sure it works 100% because you're spending a lot of money on it. If it doesn't work, it's a huge issue. So that's why you use FPGAs to test whatever architecture you're building because you can program the FPGA to change from a hardware perspective.
And so usually a lot of companies do FPGA as well because before they send it to TSMC, the turnaround cycle is like so long. This turnaround cycle cost them millions and billions of dollars of losses. When TSMC delayed the NVIDIA latest Blackwell chips, they lost so much. Yeah.
About 8 billion.
8 billion.
Yeah, for 4%.
Yeah, it's insane. All right. So now let's get into your startup. So I saw that what you guys do is basically it's PIP for hardware engineers. That's how you market, right?
Right.
So you guys look at the Verilog and syslog files and create README and you automate the process. Can you break that down? So first of all, let's start with syslog and Verilog files. What are those for hardware engineers?
So we actually only work with System Verilog for now. So it's basically like a programming language like C++, except instead of saying int x or like while loop or like that kind of thing, what you would do is you sort of describe how data moves in your circuit. So you have keywords for like register and like wire and like that kind of thing.
Correct.
So it sort of describes how your circuit looks like. And that's how everyone in the industry, they use either Verilog, System Verilog, or a new language called VHDL, one of those three languages to, sort of describe their circuits. So what we do is we cater to people who are doing Verilog and System Verilog because that's currently very popular. And we automate like the integration of like IP. So what this means is a lot of the times when you're, making some sort of circuit, some sort of chip in your company or as a hobby or whatever, you will usually want to reuse some existing component about 33% of the time. And when you want to reuse some existing component that exists somewhere, you don't want to make it from scratch. What you have to do is you have to configure a bunch of things manually. And this configuration process is really quite hard. It takes a lot of time, even for someone doing open source things. So what we did is we created a parser, which basically automates this. You can just like pip install it, and then it like automatically like sort of connects and everything. So we use agents when scaling to enterprise things because those are more complex. But on the open source scale, we just do it purely algorithmically.
Awesome. And what agents you believe? So you said you like Claude more than OpenAI.
I do actually. This is actually I'm not supposed to because the OpenAI person that we're like talking to does not want us to like Claude more, but I guess we do. So we really like Claude 3.5 Sonnet. We found it's quite good for this kind of thing. It's quite good for programming, right? So we thought, why not test it on digital hardware design? And it was able to consistently outperform, O1 Mini and O1 Preview. And I sort of, we did it in different ways, right? If you do optimal zero shot prompting techniques, like without any chain of thought, without any prompt chaining or like literally anything, but you format it in the way Claude likes it, right? With the XML and everything. And then you do the same thing with O1. And you do it like the way O1 does it without any advanced techniques. O1 is usually actually better. But the reason why we have Claude performance is because we have 5-shot chain of thought and as prompt chaining and these kind of things to improve performance. And the reason that is useful is because it's using our own how would we design a chip kind of way of doing things, right? So we're actually able to maybe the first system that's actually able to model digital logic when instead of putting things through an LLM, it's actually able to plan its architecture using state diagrams, like finite state machines, and like actually like if you see it working, you would see like it placing a bunch of registers and like drawing wires and all of that. Basically, what a regular engineer would do before implementing the architecture. And that's super powerful. And you can see it like on training sets on data sets where you give it to Claude, questions that have 118 out of 118 mismatches, which is a 0% success rate for Claude, we have 100% success rate with. So it's really like, well, what can you do with these LLMs? Like when you encode digital logic into them, that really, yeah.
So true, because the O1's chain of thought is trained on synthetic data, as you mentioned. Yeah. And like O1 is useful for specific kind of people. And also like chain of thought can be created by anyone. Like you can just write a good prompt and you can convert basically Claude to use chain of thought mechanism before it gives you an answer, right? And based on your prompting techniques, chain of thought is not special to O1. It's just a prompting technique that can be implemented in any model.
Or I would say like, when you say like use chain of thought in any like prompt, you mean like think step by step, right? For example, like we actually don't do that. I find like having a few short examples is much better than saying think step by step, because the problem is that if you say think step by step, that's when you run into the issue where like, think step by step is a zero shot chain of thought problem, right? That is why like you're seeing the same you're seeing better performance to O1, right? Because O1 can already internally think step by step. So if you just tell Claude to think step by step, O1 is of course better. But you need to show like how to think step by step. And you can only do that with a few shot example, like, way. And you can't do that with O1. It's very weird to do it with O1. And maybe you can, like, I don't know how to do it. So
got it. Okay. Yeah. So now we got to learn about syslog and Verilog files. And can you share how InstaChip works? How do you create an agentic flow? How do you automate the process of if someone is building chips today and they want to transfer to a different protocol, you automate that process as well.
Yeah.
So how does it work?
So, well, I mean, there's a variety of things you can do. So like let's as you said, like talk about how do you integrate these protocols, right? You have one, sort of command where it's like wire is what it's called. And you have like, a module that you want to wire to. So the way, for context, the way system Verilog and Verilog modules work, they have one sort of parent module that is like your top level chip. And then inside your chip, you have a bunch of like smaller chips and then inside those you have smaller chips. So what we do is with our parser, we're able to like find all the wires and ports of an external chip. And we're able to do that for your current IP. And what we do is we sort of algorithmically connect like all the like stuff that you would need to. And we use LLMs to generate intermediate code because there's a little bit of code that you have to create that's like on top of just wiring these like, modules. So that's how, that works. There are challenges, right? Like, for example, we're only able to do that at the very basic level. A lot of the times there are super like specialized data sheets that you have to work with for like specialized protocols. And that's what, we're still working on. But at a base level, that's how it works.
About the transfer of protocols, like how do you automate that?
Let's say like you have like, one chip that's working on some protocol, and then you have another chip that's like working on like some other protocol. So the first thing you have to do is you have to like integrate the two chips before you like sort of think about the protocol base. So to do that, you basically have to connect each port on one chip to the corresponding port on the other chip. So those are just drawing wires. So we do that algorithmically by like looping through like all of the wires and everything, all the ports on like both chips. And as well as using LLMs to generate any like, intermediate
test cases
or even test cases that are necessary.
So how deep is the flow? How many LLM actions it goes through?
It sort of depends. So the way we do it is we have an LLM that generates the agentic workflow as well. So if it thinks that it will take a while, like it will make it have more steps. But again, like it's always better in terms of performance to have some deterministic plan. Like you shouldn't have it do that. So what we do is we have specialized agents that do, we have an agent that does only like connecting ports and stuff. And we have an agent that does only making like super small, like actually like, proper modules. So we have specific agents that do these really small things. And we have a master agent that can, generate the plan and do it and do more complex things, even like setting up, chip environments and like that kind of thing. And that's what we market as, the first AI hardware engineer. So
Awesome.
But I think for that AI hardware engineer to be complete, there's like one missing piece, and that's verification. So, and like to talk about verification, I think we should take a step back, right? The most time-consuming part of designing a chip isn't the design; it's making sure that it works. Only 20% of the time is actually used for like designing the chip. The remaining 80% is used to simulate it, to test it, to rigorously make sure that it works. So even though we're making an agentic workflow to automate the chip design process, once that chip is designed, the flow is not complete until we can prove to the user that it's verified and that it works. Because otherwise they have no like they have no validation that whatever the LLM is creating, it could be nonsense, right? So we need to make sure that it works. The problem with simulation is that if it's not done algorithmically, then nobody can trust it. So you can't just create test benches using the LLM, because if the LLM test benches are wrong, then you can't validate that. So it needs to be fully algorithmic. And verification at the moment is very, very lengthy. It takes weeks almost to like fully verify like just a single component. So I'm working on like a system that will accelerate that process to like a matter of like minutes or hours.
Incredible. So that's the real value, because you can convert the protocol what it's using. If you can give an example of protocols you mentioned again.
AXI to PCI.
AXI to PCI.
AXI4.
Yeah, you can do that. But testing it that it all actually works with that agentic flow is most important.
This is the biggest problem in the semiconductor industry, by the way. Like
you can see this pattern when you see the hiring practices of semiconductor companies right now. They're hiring more verification engineers for teams as opposed to design engineers. It's becoming increasingly more important because these designs are becoming more complicated.
And most of the SoC engineers also work on verification. Like that's one of the biggest thing they're working on as well, right? So you're actually eliminating that process and automating it so that you can work on more valuable things.
Exactly.
Well, I would say that's a very nuanced take. So I actually think a little bit differently, but verification is it's by far the most important thing. But two, if you want to actually gain a foothold in the market, what you need to do is you need to make design or the quality of your chip purely a function of verification. So what this means is that your designs need to be as good as how good your verification is. And that means that the things that people are doing for design, you shouldn't be spending much time on it at all. Instead of 20%, you need to make it 0%. Or like 1%. So at that point in time, people like it becomes much, more relevant, and you have a very big foothold in the market of people are using your design biz. So that's really, really important, I think. And if you want to, from a market perspective.
Correct. And there's a reason why, like even this whole industry, I was reading that even most of the SoC engineers and TSMC engineers, a lot of times they're like doing hit and trial, testing the knobs and making sure things work.
Exactly.
That takes the most amount of time. And so you're automating that end-to-end process. That's why you guys are so valuable right now.
I think at the end of the day, our ideal product would be some sort of system that has verification in the loop. That would be like pure automation. So whatever the LLM creates, using the algorithm flow that I'm like currently working on, it will be able to verify and give feedback to itself. And then using that feedback, it'll work through the whole structure again. And then it'll keep doing that until it converges to like an optimal solution.
Exactly, right? So at some point in time, we'll, create our own in-house models, and they will take into account, again, like we're basically going to do what O1 does, but we'll use verification and reinforcement learning based training to do that. Okay, yeah.
Got it. So can you share how much value is there for your product? So can you share like how many chipset companies can actually use a product? Is it Apple, Nvidia, TSMC?
Oh, anyone doing like this thing called RTL design can use our product.
Apple is doing, Nvidia is doing, Google is doing. Basically, everyone is trying to create their own chips.
Yeah. Anyone who's trying to create a chip can use our product, and anyone who's trying to program an FPGA can use our product. As long as it's digital.
I see. So what are the next steps for you? What are your future goals now?
I think one of our, or the most immediate goal right now is figuring out integration. So we have things that can like sort of rudimentarily integrate things, but we want you to use an LLM to like actually do it based on detailed protocols and detailed specifications and properly integrate like really complex modules. And that's like a huge opportunity. And then the sort of, later down the year, like halfway, like some next 6 months kind of thing, would be integrating verification in some form.
Especially, that's the most important. Yeah.
Exactly.
Yeah. I mean, once that is in the loop, we immediately outperform everybody else in the market. Like that's the limiter right now. You can generate as much code as you want using an LLM, but if you can't prove that it's good code, then it's not worth any.
Totally.
And just so like, for clarity, right? Like LLM code, like our competitor's LLM code is really not that good because we started 2 weeks ago and we already outperformed.
Incredible.
So I really think like, people really have such a bad opinion on this, right? Like if you're a chip company, right? And someone is coming to you with LLMs, you're really going to like laugh at them because it's so like stupid, right?
Yeah, that's happened to me. Like since I've gotten here, right, I've tried to speak with like other PhD people, like former PhD people from Stanford that have gone on to work at chip companies. So I met with this one guy 2 weeks ago. I told him about what we were doing and then he said, we're never going to use it.
Because they think LLMs can solve your problem.
No, because they think
LLMs are bad.
Yeah.
Oh, really? Okay, so they think that LLMs are so bad that they don't believe in you.
Even if we are able to prove to them that LLMs are good, they will never put their money in on solely an LLM. That needs to be proven algorithmically. Exactly. If that algorithmic thing is missing from the equation, then you're not going to be trusted.
Exactly.
And you beat the performance, as you mentioned, of other non-LLM solutions.
Oh, no.
You don't.
So what I'm saying is, I was like affirming Jag's point, which is that LLM solutions are so not trusted. And this is validated by the fact that some of our competitors who are doing LLM things, we outperform them after a week, 2 weeks, like just doing stuff.
Insane. That is so insane because your competitors are using LLMs and they are so contradictory in their statements.
Yeah, exactly. Right. At least if you're going to be contradictory, at least be good, right? I'm just kidding. You don't put that up.
And by the way, this podcast was only possible because of Mint Mobile. Because with Mint Mobile, first of all, that is my favorite career provider, favorite SIM card provider from the last 4 years in the US. And with Mint Mobile, currently they have a deal with just $15 per month. You can get everything unlimited text, unlimited calling, unlimited 5G in the US, which is usually much more expensive. 50% off right now, only if you check it out with the link in description below, and you can activate before coming to US, and it is eSIM compatible. So go right now to mintmobile.com/sing.
Okay, now let's talk about the college degree. So you joined Stanford and you are taking a gap year from UNC.
Right.
What do you think is the value of college degree?
I think we might have differing opinions slightly, but you go ahead first. I want to hear.
Okay. So, I think it sort of depends, right? Like, I think, if you're doing anything in the EDA/hardware space, I think a college degree is quite useful. And the reason is, multifaceted, right? Like one, if you want to develop some sort of domain expertise around the world's best people, then obviously having a PhD gives you more domain expertise. And the second thing is that if you want to do have people in the industry, if you're proposing an LLM solution and you're like some kid. So, it's like, it sort of goes play hand in hand with that. So, within the hardware space, it's quite important to have a college degree. It's quite useful to have a college degree with some very nuanced exceptions. So, beyond that, right? Like most people in your audience probably may not be hardware people. So in the broader sense, is a college degree useful? Well, it sort of depends. So what are your opportunities if you don't have a college degree, right? Like if you go to college, are you going to be better off versus not going? So I think I would be better off not going.
Not going. Wow. Because of the knowledge you have right now. If you did not, then college degree would have been better opportunity.
No, actually. So I don't think college degree is useful for the knowledge.
So it's because of the connections you have right now. Because you have the connections you want without a college degree, then what's the use of it for you, right?
Yeah, at a high level. Yeah.
How about you for Stanford?
So I thought you would be a lot more critical. That's why I want, but yeah, I think from a hardware perspective, I like 100% agree with that. We've talked to people, as well, like who are working on like similar things, like tools for chip design. And they say that it's what's giving them that credibility in the space is the fact that, well, they completed a PhD in electrical engineering. So they know, so much about the space that their customers trust them. Nobody will trust like two high schoolers working on chips. It's very hard to. But I think that beyond that, I would say that a college degree is very useful for the knowledge as well. And people might disagree with me on this, but when you take a look at other like, sorry, I'll backtrack. The knowledge that you gain from a college degree might not necessarily be useful from like what you're going into, but the tangential knowledge you'll gain. So what I mean by that is I'm going to college right now trying to study electrical engineering. But the value that I gain from just solely electrical engineering probably won't justify college for me. The value is what I get from all the tangential things like philosophy, psychology, those sorts of like fields. So when you take a look at Steve Jobs, for example, right? He created the fonts on the Mac because he took like a calligraphy class in college.
Yeah.
We might not have fonts right now if he hadn't gone to college and taken that class and have been exposed to those new ideas. The college puts you in like such a right position to be exposed to all these tangential fields. And I think it's very crucial to have that because I'm going into electrical engineering. If I have like a minor in philosophy, for example, I have such a unique vantage point that nobody else has. I'll be able to see the space from a completely new view, and that might enable me to make better contributions.
Phenomenal. It's basically at the end of the day, the experiences you have with people from completely different background. They teach you about the side that you could never have been able to be introduced to.
Right.
So phenomenal. Thank you so much, Sathvik and Jag. It was wonderful talking to you all and learned so much about the chipset industry. Your work, I hope it reaches that TAM you mentioned of $20 billion, hopefully soon. Yeah. Thank you so much again.
Yeah.
Awesome. And any advice you want to give, like a last question to anyone who wants to build from high school?
Now start now. Yeah. Don't hesitate at all. I think that people oftentimes wait for the right time to do something. The right time is now. Like that's basically it. It's very oversaid and tried, but
The lights are actually, wait, this is weird because the right time it actually is like now as opposed to like 5 years ago or 5 years from now because of AI.
Absolutely. Thank you.